So what I'm going to do, I'm going to begin today by just quickly going through the material that was in the notes last week about exploratory data analysis. I prepared a set of explainer videos that I posted last week on those, so I'm hoping you've had a chance to look through them. And then I'm going to continue on, basically. So that's the plan today. So we're going to be starting. Where are we? Okay. Right. So I'm just going to draw attention to a few things, starting on page 8 of the notes. So I talk in the notes a bit about means and arithmetic means and geometric means and so on. The main idea to get from all of that is that when we talk about an average, most people in everyday life, what they're thinking of is what's called the arithmetic mean. And in this course, I actually de-emphasise that a fair bit. The arithmetic mean plays an enormously important role in statistics. So if you want to go and study full-blown statistics, you will spend a lot of time working with arithmetic means and standard deviations. In this course, I've deliberately downplayed those because to use them, I would have to get into a whole lot of stuff about distributions and so on. It takes a heck of a lot of time, and I wouldn't really be able to emphasise what are the key threshold concepts that I want you to take away from the course, which are related to things like understanding how sampling and statistical inference works, and understanding things like confidence intervals. So I want to sort of minimise all that additional mathematical apparatus. The good thing is that if you then do go on and do a course in statistics, you will come equipped with at least a couple of the really important ways of seeing things that you need in a statistics course. So I will occasionally refer to the arithmetic mean, and I'm just going to call it the mean. All those others, the geometric, the harmonic, trimean, all those things, they have specialised uses. I'll have almost nothing to say about them. They will pop up. There will be one or two things we do in spreadsheets where they're kind of hidden in the background, and I might mention that they're there, but they're not something that I'm going to be paying much attention to, and I'm not going to be asking you to calculate them or anything like that. So a lot of the focus is going to be on the median and what we call the 5-number summary. And this is a way of encapsulating in a small number of numbers some of the most important information about the shape, the profile of data. And it was developed for the explicit purpose of being used by people who were not in a situation to be using statistical software and doing complex calculations and so on. Complete loss about the screen. I don't know what's happening there. Okay. So the median is just if you take a quantitative variable and you sort it, the median is the one in the middle. And the example that I've worked with here, mostly the example I've worked with is the set of students' marks from last year's offering of this course. And the median mark there was 65. In practice, you won't, in real life, you're not probably going to be calculating these things by hand, but if you did want to calculate them, you just have to sort the data, find the midpoint, and depending on whether it's an odd number or even number of data points, it's either going to be a data point that is in the middle, if it's an odd number, otherwise you're going to find the mean of the two middle data points if it's an even number. Now, I introduced the concepts of quantitative, or we sometimes call metric data. This is one area where I'm foreshadowing stuff, because distinguishing between things that are quantitative or metric and things that are not is not always straightforward. And the situations where it's not straightforward are very common in business decision making. We do quite a lot of measuring things, particularly things where we're getting people to rate things or make judgments about things in the form of numbers. And sometimes they are genuinely metric, genuinely quantitative, and sometimes they're not. It's not always easy to tell. There are some signs you can look for, but you can get into trouble if you just make simple assumptions. And we'll actually look at an example a bit later. But generally, when we say data is metric, what we mean is it makes practical sense to do addition and subtraction with it. So one of the examples I give is the numbers on football jumpers. As far as I know, they don't tell you anything, for example, about how good the player is. Okay, they mark positions on fields, or there's various schemes. I went down the Wikipedia rabbit hole on that one. There's quite a few different ways of figuring out what number goes onto what player, but whatever they are, it doesn't make any sense to add them and subtract them, so they're not quantitative. The grey area tends to be about ratings and rankings. So you'll all be familiar, I think, with things like university rankings. In today's news, there's a new ranking of Australian Prime Ministers. Rankings, generally, it doesn't make sense to do addition and subtraction with them, except under certain very specific circumstances, which we'll get to much later in the course. But people often do that. They will say, oh, somebody's ranking is twice as high as somebody else's. But what they're talking about there is the numbers, not the thing that's being measured. And that's where it gets messy. But don't sweat that too much at the moment. For the moment, just remember that when you see rankings, if you see somebody purporting to do arithmetic with them, you should be suspicious. Oh, sorry, you should think critically. Okay, so that's quantitative and metric. Okay, I introduced the term variable. You're probably all familiar with that. In data analysis, particularly if you do a statistics course, you probably go into it thinking you know what a variable is because you learned about them in high school algebra or middle school algebra. And then you get into statistics and they start talking about random variables. And I can remember being absolutely confused by this the first time I studied statistics. And the reason is that random variables are not variables at all. They're functions. But if you're new to all of that, you just get confused by it all. A variable is just, it's just something, we can think of it as like a container for data that is all of the same type. You could have a variable which is the one we'll look at later, the weight of chickens, okay? Every data point in that variable is the same kind of thing. It's the weight, and it's the weight of a chicken. That's all it means. So don't, I know for some people, as soon as they see the word variable, it brings back sort of nightmarish memories of algebra at school. And I'm going to try and avoid too much of that. Okay. I introduced the fact that when we talk about the size of a data set, that's just the number of data points in it. And we almost always in data analysis use the letter N, either uppercase or lowercase, to denote the size of things, and that's almost the only closest thing to a standard use of symbols that you'll get. Okay, so trying to make sense of the symbols can get really complicated. I'll try not to make it complicated, but I'm just warning you about these sort of things, because if you start looking at other sources and you might find, oh gee, this other person uses completely different symbols, do they mean the same thing? There's a lot of assumptions that people can just kind of work with that sort of thing, and if you don't have a lot of experience, that's not necessarily the case. Okay, so these famous 5 numbers, so the median is one of them. If you just know the median, it may or may not be very useful. So if I tell you the median mark last year was 65, all that is telling you in terms of the kind of spatial thinking I want you to develop is that, yep, the middle student or middle students got 65 or something very close to 65, and that's probably better than nothing. If I told you the median mark was, 45 or 50 or something, you'd probably be terrified. And if I told you the median mark was 80, you'd probably think, oh, wow, that's pretty good. But unfortunately, 65 is pretty typical for a second year undergraduate course. So the next thing we look at usually is we look at the maximum and the minimum, and the distance between them we call the range. So I think the minimum was 53 and the maximum was 92. So that immediately gives you a bit more information about the real world. It tells you that nobody failed the course. Sorry? No. Now, I'll just make a little point on the side here. Nobody failed the course, but there were some students who dropped out at the last minute. And this happens with, this is fairly normal with undergraduate courses, and it happens with postgraduate courses too. And it can be very sad sometimes. What happens, it's almost always because of some circumstances in the person's life. It is sometimes because people kind of get behind and they can't see how to catch up. And they sort of, I think, feel, I'm saying this from personal experience when I was an undergraduate, because I did a bit of this, and my best friend just had a terrible run of this sort of thing. They're too ashamed to talk to anyone about the situation. So what I want to say is, if you feel you are getting behind and you're worried about whether you'll be able to finish the course, please talk to me, okay? Because I'll try to find ways to get you back on track if you want to do that. I'm not going to put pressure on anyone, but it is sad to see students who sort of hang in for 10 weeks or something, and then what tends to happen from the lecturer's point of view is they disappear. They miss the last test or something, and you email them and they don't respond, and you can't track them down. So this is a very, very common scenario. So I'm just letting you know that don't be afraid to let me know if you're struggling with something or you're running behind. And under the present circumstances of this pandemic, I mean, everyone's life's upside down, and all sorts of issues are going on. But anyway, yes, nobody failed the course. So 53 was the lowest mark. And there were some surprisingly good marks, as we will see. So the range is just the maximum minus the minimum. It gives us an idea of what we call the dispersion or variance or whatever of the data. So once we know those three numbers, we can start to form a bit of a picture. And if I had the wretched screen working, sorry, I'm just going to try resetting the projector. So you've got a diagram there on the bottom of page 11, which just shows you the sort of fairly minimal spatial information that you get just from those three numbers. And so one thing that's fairly obvious is that the students' marks are somewhat compressed into the lower half, and they're spread out in the upper half. Okay. I can tell you from experience, they're not unusually compressed. You get various different patterns, and that's one that you tend to get. Okay. All right. Now, the next thing. Sorry. Yeah.
Just to clarify for my own understanding, does that mean more students sat towards the minimum side than the maximum side?
Yes. Yep. Sorry, no. Well, there should be an equal number, or about an equal number on each side of the median. Okay. But the range of the lower half is more compressed. So it goes from 53 to 65, and the upper half it goes from 65 to 92.
So any chance you could like illustrate that?
I do actually have a diagram on, I'm not sure how much it helps, but on page 14, there's a chart there. Can you see that? So when you look at that, you can see the minimum and the median. So the median and the minimum are in red. And you can sort of get an idea of okay, so that's a bigger distance in terms of marks than the minimum to the median.
So same number of students.
Same number of students on each
But
side,
there's more
but they're
spread.
squished on the lower end.
Okay.
Yeah,
So they have closer.
yeah, yeah, yeah. Just give me a minute to see if I can do something with this Zoom. This, okay. This is just not. All right, sorry. I'm just very frustrated by this camera thing. Okay. So the next thing we look at is what originally were called the upper and lower hinges. So the guy who invented this, John Tukey, what he used to do is he would, to explain it to people, he would get a strip of paper and he'd write the numbers on it in order, and then he'd fold them in half, and that would show you where the median was. And then he'd fold it in half again, and that would make two hinges, and that was the Q1 and Q3. that was the idea. That's where the kind of terminology comes from. So, but Q1, quartile 1, lower hinge, you can just think of that as the median of the lower half. And Q3 is the median of the upper half. So between them, they just divide the data up into quarters. That's all they're doing. I do make the point that when you actually come to use software to do this, there's a whole bunch of different formulas that are used for figuring this out. I will show you the original way of doing it, but don't worry about that too much. They all produce pretty much the same, very similar results. It's not a big deal. Okay, so if you look at the diagram on the top of page 13 now, I think the people on Zoom, you can see the projected screen, can't you? Oh, it's a canvas. Probably not getting any audio there either. Sorry, can I just get someone to say something?
Hello, yep.
Okay. Yeah, we've got all sorts of audio shenanigans as well today. Okay, so top of page 13, that now shows you the Q1 and the Q3. So when you look at that, there's a couple of things you would notice. One is that the distance between Q1 and Q3, we call that the interquartile range, the IQR. We see that that's fairly small. I think it's about 9 marks or something like that. So half the students are in there. Half the students are in that 9-mark range. And that, again, is actually not unusual. That tends to be where students are concentrated. The other thing you notice is the distance between Q1 and the median is very small. So there were actually a lot of students that had marks that were between whatever it is, 63 and 65. There's a bunch of students ended up, 1/4 of the students pretty much ended up with marks in that range. All right, so that's the basic mental picture. Now the next thing we get interested in, and we always are interested in when we first get some data about something, is, well, there's two things. One is any data missing? In real life, in many situations, there will be missing data. And you have to, that can be a real headache. You basically have to go and chase it most of the time, see if you can get it. But sometimes it's just missing because somebody didn't record something, or they made a mistake, or some electronic sensor stopped working, or, you know, there's many, many different reasons. The problem with missing data, and it's not something we're going to really go into in this course, but if you are doing more sophisticated statistical modelling, many kinds of statistical procedures won't work properly with missing data. And so what you have to do is make a decision about what to do with it. Okay.
Ed,
Yep.
I just noticed something in the formula. I think it's on page 15.
Yep.
The UF equals Q3
Yep.
plus 1.5 times IQR, but then it goes, in our case, it's 72. But shouldn't it be 73? The Q3 in the formula?
Quite possibly. What have I got? I've got 72 for the upper hinge there.
But it says it's 73 in the on page 14, or 72. Sorry.
So 72, and I've got, what have I got? 73, have I?
I know. I read it wrong. Sorry. That's my fault.
No, that's all right. And don't worry, feel free to find my mistakes, because I do make them. And I appreciate being told, so don't worry about that.
Yeah, sorry about that.
I make lots of mistakes. I do my best to correct, you know, but okay, where was I? Missing data, yeah. So when you, for more sophisticated, you know, this is this, I'm talking here about the step where essentially you're looking at data that you perhaps haven't seen before, trying to make sense of it, see what it's useful for, what it might tell you. Then the next step is you would do some kind of data analysis, statistical analysis, or whatever. A lot of the procedures that are used don't like to have missing data. And so your options are either take the missing data out, take the observations out, or there are a whole lot of ways of trying to have a guess at what the missing data might have been and make it up. Okay, and there's a whole literature on that subject, and there's all kinds of software for it and so on. But whatever the story is, missing data is something that you need to pay attention to. The second thing, and the thing that we're going to focus on, is outliers. So outliers are unusually large or small data points in a variable. That's the simplest form of outlier. So there are actually much more complicated forms of outlier, but this is the most common, and the first thing you look for is to see, are there any, you know, weirdly large or small. In this, we're looking at marks. So what I can tell you from, because I've been a second examiner for hundreds of courses over the years, it's pretty common to get outliers at the low end. So you'll have a course where nearly everyone passes, but there'll be 2 students who got 20 or something. And it is almost always because they didn't submit all the assessment. Students who submit all the assessment rarely fail. The exception might be courses that are, you know, 70% of the marks are sit-down exams or something like that. But certainly in my school, where we don't have a lot of really big exams, the most common reason for a low-end outlier is not completing all the assessment. But you want to check and see what went on. At the high end, it's reasonably common to get a few outliers at the high end. It depends a lot on the subject. So in this subject, this is my third time teaching it, we've always had some students who are doing double degrees and they've already done 1 or 2 or 3 statistics courses. And so anything that looks like mathematics in this course is a breeze to them. It's just totally new. And we also get some students who are really super bright. So it's not unusual in this course to get some students that just sort of totally ace it. But there is an interesting point I'll make about this a bit later. So how do we find outliers? Well, there's lots of ways of doing it. The method that I'm showing you is one that came with the invention of the 5-number summary and its graphical form, the box plot. And it's probably one of the 2 most widely used. The other one involves means and standard deviations, and that actually has problems. The 5-number version that we're using here, I think, is better, at least for a first attempt at finding outliers. So what we do is we have our Q1 and our Q3, and we have an interquartile range, which is the middle half of the students in this case. And what we do is we calculate the location of what we call the fences, the lower fence and the upper fence. And the idea is that anything that's smaller than the lower fence or bigger than the upper fence is an outlier. And the standard calculation we use is that for the lower fences, you take Q1 and you subtract from it 1.5 times the interquartile range. That is Q3 minus Q1. And for the upper fence, you do the same thing, but at the upper end, so by adding. So you add 1.5 times the interquartile range to Q3. And so we find those 2 numbers, and then we look at anything that's smaller or larger. And what you're looking for really is to see whether there's the outliers are the result of something going wrong. Okay, so with student marks, one thing we would just check is that all the marking was done properly and everything was added up correctly, and we do that anyway if a student gets a mark below 50, so everything gets looked at by a second examiner and so on. At the high end we might check as well, but we usually don't worry so much about that because we do expect to get some very high performing students. But in many other kinds of situations, an outlier could be the result of somebody put a decimal point in the wrong place, somebody, I don't know, multiplied when they should have added, or, forgot to carry 1, or, there's all sorts of some instrument misbehaved. There's lots of reasons why you get outliers. And so you always want to check them because they could be wrong information. Another thing they could indicate is there's something going wrong with the process. So this is in something we'll talk about towards the end of the course, statistical process control. One of the things that we're interested in is typically in manufacturing processes, but also in service industries, an outlier could indicate that something is going wrong. So for example, if what you're tracking is, say, hotel check-ins, and what you're measuring is the time that passes from a customer coming, someone who's staying at the hotel, coming in the door, through checking in and arriving at the room, and you measure that, you take a sample of that every day, and hotels do this. If you suddenly get outliers in that data at the high end, that can suggest something is going wrong with the check-in process, or something is going wrong with having the room ready for the customer. So you watch out for outliers. If the outliers are real, they're not the result of something going wrong. There could be something going wrong with the process, but if they're not the result of a data recording error or a calculation error or something, then they can still be a bit of a problem, because those same statistical processes I talked about, or procedures, that are affected by missing data, they tend to be affected by outliers as well. And so you need to know they're there. You need to be aware of them, because you might have to make some choices. Common sort of thing you might do is you might do the statistical analysis with the outliers in the data, and then you try it again with the outliers out of the data to see if there's a big difference. If you get pretty much the same result, then you're sweet. If not, kind of back to the drawing board. So outliers, really important. That 5-number procedure with the fences, that actually works pretty well. It was very carefully thought out when it was developed. Okay. The chart that I've got on page 14, I'll just make one other observation about it. If you look at it and you kind of squint, it looks vaguely S-shaped. And that is a shape that we expect with students' marks. So, and this is what I mean about spatial, geometrical thinking. We know from long experience and lots of studies that typically a set of students' marks is going to look something like that. It's going to be vaguely S-shaped. And if it's a really weird shape, if it goes like that or something, something's probably gone radically wrong. Things don't usually go radically wrong, but to give you an example, the sort of thing that could go wrong would be if you had two people doing the marking and one was really tough and one was really easy. Another thing that can distort it is if you have a lot of group work. If you had 70% group work in a course, that's going to create a weird shape, because you're really measuring two different things. You're measuring groups and you're measuring individuals, and they tend not to be correlated. But that's a story for another day. Okay, so there we go. So in the case of our student marks data, we had, there are about, 9 outliers. Now, what turned out to be the case with the marks last semester, and I haven't really come across this before, but in the top 20 students in the class, so this is out of 72, something like 16 of them were people that had pretty regularly turned up online for the 3-hour seminar thing. And I did all of the marking blind. So I didn't have people's names on things that I was marking, and some of the marking was done by a teaching assistant as well, and also done blind. I'm not saying this to sort of lean on you to attend classes online or in person. There is there've been lots of studies of this, so that in the normal kind of lecture theatre situation, and the studies will all tell you that students who turn up to class do better on average, and students who sit at the front of the room do better than the ones who sit at the back. But nobody really knows whether that's cause or effect. Nobody knows really whether it's just students who are highly motivated and ambitious for high grades or something come to class and sit at the front or whatever. But it did surprise me a little bit, because I wasn't expecting it to be quite such a strong effect. So there you are. All right, so now, how are we going for time? Can we let's just take a break for 5 minutes or so. I'm going to have one more go at trying to fix this projector, and then we'll move on. So this is what we end up with. We have our minimum and maximum, our median in the middle, and then our two quartiles. And then I've put these outliers here as little circles, and as I point out there, I've done what's called jittering to them. So we do this quite a lot when we're doing visualizations of data, and we've got things that would otherwise sit on top of each other. So if I didn't jitter them, it would just look like you had 3 outliers. That's all that it means. But I will always point out to you when I do that. So that's the set of numbers, but what we typically do, and certainly what I do, is I pretty much go directly to the visualisation, and the standard visualisation of this 5-number summary is a thing called a box plot. And my guess is you've all encountered this, and some of you probably had to laboriously draw them by hand, and until quite recently you couldn't do them at all in Excel without kind of manually building them from boxes and things. There was a campaign over about 30 years to get Excel to put box plots in the charts, and when they did it they made a mess of it. They're not actually, well anyway, I'll come to that later. Okay, so we're going to move on to, we're going to sort of move backwards and forwards between some data sets here. I've introduced another data set here. This is about fattening chickens. So this is from a real study that was done quite a few years ago on an agricultural research farm place, and they were interested in the effect of some food additive, probably a hormone, I don't know what it was, in increasing the body weight of chickens. So they took, little young chicks, and some of them got fed their regular feed, and some got the feed with the additive put in it. And when they were mature, they were weighed, and this is the data. So just a couple of things to a few things I need to point out here. So just looking at the data table, I'm going to talk in more detail later about this, but this is data that's in what we call tidy format. And so what it means is you've got a unique identifier for each thing that's being observed. So it's the chickens that are being observed here, we call them observations. And each row corresponds to an observation. Each row is a chicken. And then you have two variables. The variables are in columns. So we've got a variable which is the weight and a variable which is the group. And the weight variable is a quantitative variable. So weight is one of those things that's genuinely quantitative. And the other variable, the group, is what we call, we have a bunch of names, but categorical variable, which is probably what I will mostly say, but other people call them, in psychology especially, nominal variables. And sometimes they are called factors, which is confusing because there's another thing in statistics that's called factors and it's totally unrelated. So you've got two variables there. This is let's just have a quick go at the calculation. I think is the best thing to do here. We've got, how do we work out the 5 numbers? Well, let's look at the control group. So I've sorted, within the control group, I've sorted them from highest to lowest, and I've done the same for the treatment group. So it's pretty easy to pick out the maximum and minimum. So the maximum for the control group is 1.81, and the minimum is 1.70 kilograms. So that's easy. We've got odd numbers here. We've got 8 chickens in the control, even numbers rather. We've got 8 chickens in the control group and 8 in the treatment group. So there isn't going to be a single chicken in the middle, there's going to be 2. So we're looking at the middle 2 for the control group. They both have, no they don't. One is 1.76 and 1.7, the other is 1.74. So we need to find the mean of those two numbers, which is 1.75. And that's the median. And then for the treatment group, it's 1.86 and 1.84, so the median is 1.85. So that part's fairly easy once you've got the hang of it. Now, what do we got? 1, 2, 3, 4. So we've got 3 and 4, so it's 1.85, isn't it? Oh, hang on. It's the middle 2, so... Oh, you're right, sorry. Oh dear. Hang on. Let's go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Oh, you're right, it is 2. Gosh, did I propagate that mistake all the way through? I hope not. No, it's okay. You're quite right. The mean of 1.84 and 1.82. Okay, it's 1.83. So that's the median. Now, to get the quartiles, this is where there's all these different ways of doing it. But the original way is that you would look at the upper half. So I'll just do it here for the treatment group, okay? And I'm doing that because I'm pretty short and I can't reach the control group. Because we have an even number in the upper half here, that's all we take into account. We just take into account the top 4 here. And so that's also an even number, it's 4. So the middle we've got 1.87 and 1.86. And so Q3 is going to be 1.65, yeah. And then it's similar for the lower half. So we just look at the lower 4. We've got 1.80, 1.79, so it's 1.795. Where it gets trickier is if you've got an odd number in the lower half or the upper half. But I think we'll deal with a case like that when we come to it. I won't worry about it now. It's better to look at an actual example. So on page 19, I've got the numbers there. I've also worked out just for comparison, the mean. And the total weights. Now what you'll notice is the means are very close to the medians. Yep. Yes? Sorry, was that a question? No? Okay. Yep. So you'll notice here the mean's very close to the median, and that is another thing actually that we look for, because that tells us a little bit about the shape of the data too. But we'll see examples of that as we go through the course. Don't worry about that very much at the moment. All right. Let's go back to our marks for last year's course now. So what we have there is a box plot. So this is what we call a canonical box plot. Canonical means it is the one true established way of producing a box plot. I'm being slightly facetious about that. People like to invent new ways of doing it, but this is the standard box plot representation of the 5-number summary. Except that we don't normally show the fences. So the vertical dotted lines there are the 2 fences. I've just put them there because I want to illustrate something about them. So what you have in a box plot is you have a box, and one end of the box is Q1, the other end of the box is Q3, so the width of your box is the interquartile range. So we know that half the students are in that interquartile range. In this case, this is a horizontal one. The height of the box in the standard version has no meaning. Okay, it can be as thick or thin as you like, and it's often useful to have very thin ones because you can compare lots of variables. We'll see examples of that later. And then you have some way of marking the median. So sometimes it's a vertical line through the box, sometimes it's a dot or a cross, triangle, whatever. But there's some sort of a marker in the box for the median. Yep. No, that's okay. And then you have these things called whiskers that come out the side. So and this is probably the trickiest thing to understand about the standard box plot. So the whiskers go to the largest, we'll start with the left-hand side one here. This goes to the smallest data point that is not an outlier. Now in this case there are no outliers at the lower end, so the whisker is going to the minimum. So the fact that we don't see any outliers here means that that is going to the minimum. And this little thing on the end of the whisker is called a staple, but almost nobody knows what that's called. You're in a very elite group now that you know that the line on the end of the whisker on a box plot is called a staple. And I imagine that John Chuka used to staple his piece of paper or something to mark it, I don't know. Now at the other end, what happens here is we do have some outliers. So the whisker is extending out just to the point of the largest data point that is not an outlier. And you'll see that's just below the upper fence. And then you have the outliers. So you know when you look at that the maximum is going to be the furthermost outlier. So that's really the trickiest thing about interpreting a box plot. Now, you get some variations on this. So there's one fairly common variation which just ignores the outliers. Okay, so that version will extend all the way out. You won't see any outliers even if they exist. The whisker will just go all the way out. So in many types of software, that's an option that you can turn on or off. You can tell it to show outliers or not. So some versions of Excel do that. Some will allow you to turn it on or off. Some versions will by default have it turned off. Some will by default have it turned on. Some software, well, Excel's the only one I know of, calculates Q1 and Q3 using the non-standard method, a non-standard method. Doesn't matter most of the time, but they don't tell you that. There's no documentation to tell you that it's non-standard. Some software calculates what things are outliers or not by using the quartiles and fences, but by using means and standard deviations. Some versions of Excel do that. The only version of Excel I've found that does it absolutely correctly is the Chinese version. So the current Chinese version, it seems, we did some, when I taught a class in China last year, we did some tests. And for some reason, the Chinese version that my Chinese students had produced an absolutely standard canonical box plot. But I tried a few different English versions and no, that's weird. The Mac version was different to the PC version, and so the problem with that is it's really just you want to know what you want to be able to be sure that what you're producing, you want to be sure what it's showing. That's all. And if there's nothing to tell you, it's just kind of weird. So you just want to be aware of that. But that's a box plot. The other sort of variation, sometimes people will make the height of the box plot proportional to the sample size, to the number of, in this case, students. There are sort of tweaks like that people do. Another very common one is to, as well as the median, to show the mean. And that, I think, is quite useful. So sometimes you'll see a line for the median saying a little cross for the mean. And that can be a useful thing to include. So just be, sort of mindful. I'll just mention here a kind of bigger problem with this course that I haven't got a solution to yet, and I'm not sure if I'll find one. I'd love to be able to say to you, here's some great software you can all use and you can draw all these charts real easy. But I don't really know of any. I'm hesitant to recommend Excel. You can do it in Excel with a lot of work. It's very slow though. But I do all this in software that has a pretty steep learning curve. It's very quick. I can knock up these charts in a few seconds. But I've had 20 years experience and I've been down the learning curve. I think probably the best candidate is going to be something called Tableau. Has anyone used that? It gets very positive reviews from experts I trust on data visualization. But I haven't used it myself, so I don't really know, and it costs money, I think. I don't think, well, students may be able to get a student version, but I'm going to give a bit more thought to that question. I have given you a link to a website where you can draw a canonical box plot, if you want to do that. So that's the basic box plot. What I want to move on to really is some examples of how we use it. Okay. I just thought I'd show you a vertical one. You'll notice I mostly use horizontal ones, and the reason I do that is partly I think most of the time it's easier to compare box plots when they're horizontal, but it's also from many years of writing reports, and horizontal box plots don't take up much space. That's often the main reason I don't use pie charts, because they take up a lot of room. That is a story we will get to later in the course. So you can see with this one, it's vertical, there's no staples, and I've used a diamond to show the median, but it's still a canonical box plot. It's got the outliers, everything was calculated in the same way. So you can get variations. There's a version of a box plot which is extremely narrow. It's just a line. It's got a couple of spaces where Q1 and Q3 are, and a dot where the median is and the outliers. And you could fit 100 of those on a page. You know, if you wanted to compare, I don't know, sales from 100 outlets or something, or 100 products, or you could do that. But that probably leads me to just one other caveat about box plots. Is a lot of people out there in the world don't know what the hell they are or how to read them. So you need to be, what we're looking at here is stuff you do in the privacy of your own home or office. When you start presenting to an audience, to a client or to people in your organisation, you've got to think about how well your visualisations will actually convey your messages. And if you're showing a bunch of box plots to people that have no idea how to read a box plot, it's a waste of time, and they won't appreciate it. I have been in situations where I've done work for the government and I've presented stuff as box plots, but I've done it in a situation where box plots were just really the best way to show the data, and I was able to spend a bit of time explaining to people how to read them, how to understand them. So you can do it, and increasingly people know. So I'm pretty sure in Australia box plots are in the middle school curriculum. I think you'd probably do them by the end of year 10, is that? Yeah. Whereas, well, they hadn't, are they? Yeah, they'd sort of been, yeah. The canonical box plot hadn't been published when I was in school. And I didn't hear about it until 1998. But yeah, so more and more people will know about them, or at least can be reminded, you know. Okay, I've just mentioned the word frequency there, so you hear that all the time when people are talking about statistics. It just basically means how many of something there is. Okay, now I need to talk to you a little bit about tidy data. So there probably is going to be a test question about this. It might sound like nitpicking, but this is one of those things that I know from long experience is really useful. And that is when you get data and you're going to store it, and you can store it, you know, Excel is not a bad place to store data. It's one of the, I mean, I use Excel every day, and one of the big things I use it for is just storing data, sorting it, things like that. But I really recommend that in most cases you get the data into what we call tidy format. If it's coming out of a relational database, the sort of standard kind of database setup, it probably will come this way. But these days data comes to you from all kinds of sources, and some of them produce all kinds of interesting things. So I've described some of the main features. So if the data doesn't have an identifier for each row, so each row should contain measurements or information about a single observation. In this case, it's chickens. It could be online shopping transactions. It could be performance ratings of staff, whatever it is. A row is data about one individual subject of some sort. And then what I strongly recommend is that when you get the data, when it comes to you, so to make this concrete, I get to check a lot of grade sheets. Okay, so at the end of a course, grade sheet gets submitted, gets checked by various people, including me. As soon as I get a grade sheet, what I'll do is I will put my own identifier in the leftmost column. And the reason I do that is because I'm then going to be sorting things and whatever, and it is sometimes just useful to be able to resort and go back to the original order. Okay, you know, you get a phone call from the lecturer who says, "Oh, I made a mistake with the one that's fifth from the top." Which one? You know, student numbers usually take care of that, but it's just a little precaution that is worth doing because it will one day pay off, and you'll be so glad you did it. So, but quite often data will come with a unique, whatever you do, there needs to be a unique identifier for each row. So with student data, it's always the student number. But even that sort of thing, you've got to be careful with, because student numbers, sometimes, our student numbers sometimes come with a U in front. You know, U 1, 2, 3, 4. Now that's great because that makes it a character string in Excel. And Excel won't try to, you know, round it or turn it into a date or turn it into scientific notation or something. But if it's just a number, which is actually the standard way that they are used internally in ANU, Excel might do that. And that can create a problem. You know, it's a bit scary when suddenly your student numbers have all turned into scientific notation and you think, holy hell, you know. So you just got to be, you know, it's just something to check. Make sure you've got a unique ID, and I would just recommend always putting in some sort of something that will enable you to go back to the original sorting order. There's some other requirements that are fairly, you know, probably don't really need to think about, but they actually will come up in real life. So each cell should only contain one bit of information. So what you sometimes will get is, you know, you get a mailing list or something, and it's got a cell which is called phone number, and then what they've got is two phone numbers in there with a slash in between them or something. And suddenly it's not, for some people in that table, it's not a single phone number. Or they'll have phone number and email address or something stupid, you know. So that's forbidden in a tidy table. Has anyone here studied computing? Relational databases? Okay. What we're looking for is something called Boyce-Codd normal form. Which if you're learning databases, you'll learn normalisation, and BCNF is a kind of level of standardisation of tables in a database. That is, nobody else should even think about that. But if I just thought, there probably are some people in the class that are familiar with relational databases, and that's actually what we're looking for. Now, what happens with this tidy format is if you've got a lot of data, it's going to be a very long table, and it's not a readable table for visualisation purposes. So if you wanted, so this data, for example, it's not terribly long, but probably if you were putting it in a report just so people could see what was going on, you'd do that to it. So we call that unstacking. So this table is said to be stacked because you've got the control observations stacked on top of the treatment observations or whatever, and here it's manipulated and turned into columns. So that's not in tidy format, but that's a much more usable format if you've got a message. So if you're putting this in a report and you're saying to the reader, hey, look at table 3, you will see that most of the chickens that had the food additive were heavier, or on the whole, the chickens who had the food additive were heavier. People will look at that and they'll pretty much be able to see that. And they'll be able to see how many chickens there were, and, you know. So sometimes when you're writing reports, you will have data that you want to use as a visualisation in a table. And you put that in one format, maybe like that. And you may also feel that you need to provide the raw data in all its glory. And so you put that in an appendix. Okay. Again and again and again, I see presentations, and not just from students, but from academics. Academics are terrible at this. But I'll show you some table, and it's just, you know, everything's to 6 decimal places, and you can't make any sense of it. They'll tell you that it says something, but you couldn't do anything with it without copying it and pasting it, putting it into some software and figuring it out. So what you learn to do is if you're going to use a table to reinforce a message, you present it in a way that will do that. And I just mentioned here the concept of effective digits. We will talk about that later in the course. But the idea, I can just quickly illustrate the idea. The idea is that in this case, all the numbers start with 1. So 1 is not telling you anything about how different they are. You've got to have it in there. What you're interested in is the digits that are different, and that's these two, the two after the decimal point. But if you happen to have weighed your chickens to 6 decimal points, that would be too much information. You'd be better to just round it to 2. And you'd make a note that this is rounded perhaps, but for the purpose of conveying a message, you think, okay, what's the reader going to look at? How many effective digits do I need? How should I sort it so that the message is as clear as possible? It's just a different way of thinking. All right, so there's the box plots of the chicken data. I talk a bit there about randomised controlled trials and so on. We will get to all of that later in the course, so don't worry too much about that now. I only mention that because this data was part of a properly conducted experiment, and so we can take it fairly seriously as evidence of causation. That's what we'll be coming to later in the course. When we look at 2 box plots like that and we see that the box on one of them is entirely above the box on the other, then we can be pretty confident that there's a real difference, that the difference is real. And we'll flesh that out later in the course where I do explain it here, but what statistical significance means. So if we look at that, we know something about how the data was created, collected. We can conclude that there's a statistically significant difference. And what I would like you to start remembering now is that because something is statistically significant doesn't mean that it's big or important or meaningful in the real world. You can get things that are completely trivially tiny but are statistically significant. In this case, the difference is about 80 grams on average. That's not completely insignificant in the real world, but it's not like, you know, the chickens that had the food additive were all sort of big bruises, and the ones without it were the little shrimps. It's a small but probably commercially important difference. To work out if it's actually important in the real world, you've got to know about the decision-making context. And I give a list down there of some of the kinds of things that an actual decision maker would want to take into account. That experiment gives you some confidence that the food additive works, that it has an effect. But you need to know things like how much does it cost? You know, how much more money we will get for that extra 80 grams per chicken. They're the sort of things that you have to take into account. What if the extra weight is all feathers? Maybe the hormone just makes them fluffier. And, you know, there's things like that. So that's about the real world, and you've always got to keep that in mind. And this is something we'll come to this when we're looking at the academic articles and the tutorials too, because sometimes you'll get an academic article where the author is terribly excited about this wonderful statistically significant thing they found, but when you figure out what the actual effect in the real world is, it's not worth worrying about, you know. So you have to learn to think that way. I mentioned some stuff there about precision. Do not worry about that now. We will go into that in a lot of depth later. But the general principle is the more precise a result you want from this kind of experiment, the more chickens you've got to experiment on. And in the real case, this was actually one of 18 experiments that were conducted simultaneously around this farm. Okay, now I had a beautiful data set which was about butter fat in the milk from dairy cows in Canada, but I decided to do skateboarding instead. I know about as much, I probably know more about butter fat than I do about skateboarding. But I thought this was quite interesting. So let me start by saying that I really do not know much about skateboarding. So if I say something that makes me look like an idiot, please tell me for future reference. So some of you will know that the women's skateboarding finals were held last Monday, and the two of the medals were taken out by competitors from Japan. The gold and the bronze, I think, and the silver was a competitor from Brazil. And the gold and the silver winners were quite young. They were 13 years old. And I, for the purpose of preparing this, I managed to get hold of a video of the finals and watched it. And it was actually quite an exciting competition because it did sort of turn on its head as it went through. But the basic setup is the way they compete. They don't race or anything. What they do is each competitor does a couple of what they call runs. So it's 45 seconds of zooming around the course. This is street skateboarding, so it's kind of set up like the stuff you would find in, you know, inner city Melbourne or somewhere. And then I'm not sure if they have to, but they all do what's called a trick in the middle of it, which generally involves flipping the skateboard in some way and landing on it and not falling over. Okay, but the run part of it, this is all about demonstrating their grace and flow and skill and ability to recover from a leap and all that kind of thing. And it's very visually impressive. The second part of it is they get 5 attempts at just doing a trick. So typically what they do is they take off, they grind down some sort of a rail, and they flip the skateboard in some way. And it happens really fast. So if you're like me and you have no idea what these tricks are, you hardly see it happening. I'll show you a video in a moment, but you hardly see it happening. It's only when they do the slow motion replay you realise, my God, how amazingly talented these people are. It's pretty impressive. So that's what a scoring sheet looks like. You'll see that there's some numbers that are crossed out. They have a pretty complicated system of scoring, which involves deleting high and low scores and various things. The final score is calculated from 4 average scores that are left. But we're not actually, for this example, we're not going to bother with that scoring system. So let me just get the share going back. All right, so look, basically all of those contestants would already have sponsorship deals, and they will get better deals because they were in the finals, and the winners, of course, will get fantastic deals. But let's just imagine that you're perhaps interested in getting one of these, signing them up for an advertising campaign to attract young tourists to Melbourne. So Melbourne apparently is one of the top places in the world for street skateboarding. And it used to be the case that Canberra was one of the top places for park skateboarding, which is the other version of skateboarding. I didn't check that one, I don't know if it still is, but apparently we have a lot of great skate parks. Some sort of legacy from the 1980s or something, or maybe the 90s. Anyway, so what you'd want there really is someone that's going to look good doing runs, because what you want to do is you'd have them zooming around Melbourne tourist hotspots on their skateboard. Marvellous as the tricks are, as you probably noticed, you can hardly see them. And you know, expert people who skateboard would look at them and, you know, think, oh, yeah, well, but not everyone else. So, so what we're interested in here is the runs, not the tricks. And so what I've done is I had to manually copy the data, and I've put it in a table here. Is it a tidy table? Well, it's got its lovely sequence preserving IDs down there, and then each row is an observation about one. It's actually an observation about one run, so that each person gets 2 runs. Each one is an observation about one run for one athlete, and it's, you know, everything's nice in the cells and everything. So that's a tidy table, and it's quite a long table because altogether there's 80 data points in that. Okay. Goofy means you stand on the skateboard with your right foot forward, and regular means your left foot forward. And I can't for the life of me figure out what I would do. I'm sort of semi-ambidextrous, and yeah, and I own an electric scooter. I ride it, and I haven't ridden it for about a month, and I can't even remember whether I'm goofy or. I think I'm regular on the scooter, but it's weird. Anyway, that's by the by. So that's the data. We've got, when you look at these variables, there's only one metric variable here, which is the score, and the rest of these are categorical variables. So the name of the athlete is a categorical variable, whether it's run 1 or run 2. I've used letters to indicate the judges. There's 5 judges. There's the country and there's the stance. So they're just categorical variables. Okay. Now, I'll just make the point, we'll explore it a little bit in a moment. The judges' scores are ratings. So this is a person looking at something and making a judgment about how good it is and giving it a score. That is the most common kind of data, which could be metric or could not be metric. Okay? And we will go into this in more detail later in the course, but as soon as you see anything that looks like rating, so same with marking essays or something, there's human judgment involved. It could be metric, it might not be. One of the reasons that we really strongly encourage lecturers now to use rubrics for marking things like essays is that if you use a rubric, a well-designed rubric, you're much more likely to get metric scores. And you need to get metric scores, because what do we do with scores? We add them, subtract them, multiply them, work out GPAs, all that sort of thing. So you want that data to be metric, but it isn't guaranteed. But let's have a look and see what we get. I can tell you I think it is fairly metric. Just going by instinct and experience, I think it is in this case. So there's the 5-number summary. First thing you notice, and we'll see it in a moment on a box plot, is there are some outliers. So what you have there is that's a box plot for. Just enlarge that a bit. Oops. Come on. Okay. That's just all the scores turned into a box plot. And so we've got a bunch of outliers down there. They are not jittered. It turns out that, so of course we'd investigate them. So we noticed 2 things. One is the outliers, so we've got to check those out. The other thing that's a bit interesting about this is the scoring is meant to go from 0 to 10. So 10 is the maximum score you can get. And you'll see that the highest score here is a bit less than 4, it's 3.9 something. Why? I actually don't know the answer to that. And I haven't been able to find an answer. It could be that, okay, this is the first time this sport has been in the Olympics, and maybe the organisers thought, well, we need to make allowance for the possibility that, you know, real superstars will emerge in the future who can do things that we never thought of. I don't know, but the scores seem very low, and I don't think it's because these are particularly bad skateboarders. I haven't actually checked the men's scoring to see if that's significantly different, but anyway, that's so if we take that box plot and we stick it on over the full scale from 0 to 10, that's what it looks like. And this is the sort of thing you need to think about when you're doing exploratory data analysis, is just making sure that when you're visualising things or you're looking at them, that you're thinking in the right scale. So that sort of makes it very clear that, you know, I think you'd have to say there's no way that 5 is like a pass mark or anything on this scale. Can't imagine it's conceived like that. My guess is that the judges use some sort of rubric. And one reason I say that is the scores are to 2 decimal places. And so if you imagine a scale from 0 to 10, 2 decimal places, that means that you think the judges are capable of categorising people on a 1,000-point scale. Nobody can do that. So I think what's happened is they're using some sort of a rubric, probably on a computer, because they're doing this very quickly. And the rubric involves weighting things, and so you get multiplication and stuff, and that's why you get decimal points. So the second decimal point is probably noise, really, but that's what you get. So, okay. So the outliers are all from this competitor, Nishimura Aori. So she just had a really bad run there. She's a world champion. Sorry? Did she get? No. Well, no. She was. So there are other competitions predating the Olympics. So there's the X Games and there's another one, and she, I think, won both of them, and one of them more than once around 2017, 2018. So she's a pretty high level, very high level competitor. But she just totally fluffed that run. The next run she did really well. It's just very sad, but that's what happens, you know. But I think she did badly in the tricks too. I don't know the whole story. I think she might have been injured or something. Oh, well, she might have well have injured herself then. It's a brutal thing to train for, this, because you spend most of your time falling off. Anyway, so what we see there is just going back to this. So what we're seeing there is those outliers are, sorry. Okay, back again. So those outliers are just from that run for her, okay? That's all they are. She just got very low scores for that. Okay, so that's, okay, yeah, so I've done box plots for her scores for the first and the second run. So you see for the second run, she was well up. Now, the next thing I was interested in was, what about these judges? You know, how consistent are they? I'm very familiar with judgments in the form of people marking assignments. You will never see that much consistency. You get 5 tutors marking assignments. You won't see that sort of consistency. If you're doing a job properly as a course convener, you will make adjustments so that students are not disadvantaged according to who marked them. Okay, that is, to me, that's extraordinary consistency. I don't know how they achieve it. I haven't been able to find out what actually goes on, whether they all sit in a room and they just, but they do it really quickly. You know, you saw they had in the video, they had the score up within 30 seconds or something. So I can't imagine they spend time chatting about it. They must just be really all on the same page in terms of what the criteria are or something. But this is one of the reasons this would give me a bit of confidence about this being metric data, is that there's really quite clear consistency there. Sorry? This, this one. So this is the video I just showed you. Those are the outliers. So every judge gave her a very low score on that run. But otherwise, you know, they're all. It's really, you couldn't. You know, I'd say looking at that within what we think of as the kind of margin of error there, they're all very, very consistent. There's, when I started, I did go a bit down on the rabbit hole of Olympic scoring, and boy, but a lot of it stems from the Atlantic Games. There was a huge scandal about figure skating. That's probably might have been before most of you were born. I can't remember now, but it was a big scandal because there were some judges who were bribed and leaned on to favour the Russian. I think, I don't want to defame Russia, but I think it was the Russian. And that's led to a whole lot of new governance rules and... Sorry?
Ed, like the dotted line, the broken line, are they the whiskers that you talk about?
Yeah, so these are the whiskers here.
Oh, yeah.
Yep, so all you've got, so all the other scores are between the whiskers, and then you've just got these, you know, really very extreme outliers.
Okay, so that's how you express those 5 points of data pretty much, those 5 bits of key
information. Exactly. So the ends of the boxes, they are Q1 and Q3, the quartiles, and the coloured blob there is the median.
Okay, yep, I get it. Yep.
So the minimum is going to be the smallest outlier here, and the maximum is going to be the end of the whisker at the other end.
Oh, yeah, I get it, yep.
Yeah, once you get the hang of it, you'll start looking at box plots and you'll sort of begin to, you know, develop a picture. So I did some more, I'm sort of showing off here. I'm just trying to show you the kinds of things you can do to explore the data. So this is a bunch of box plots. These are combined together in what we call a trellis plot. So what you've got there is, in the lower row of box plots is the scores for the first run. So you've got a box plot for each competitor, and the box plot shows the 5 scores that they got from the judges. And then the top row is the scores for the second run. So you can look at that and it'll give you an idea of who performed better in the second run rather than the first run. And you can also get an idea of how close the scores were. So what really stands out there is that the scores were really close between the judges for each candidate for each run. The biggest sort of variance was for Zwetsloot here, who got the, you know, very high score in her first run. The biggest improvement, obviously, was Nishimura, who went from that disastrous first run to what was really a very good run the second time around. So that's all that tells you. But once you get kind of intuitive about reading box plots, they're just a very good way of doing this kind of preliminary exploration. They're not the only plot you can use. We'll look at another one next week, but this is one of the main ones. And then the last thing I think I have here. Okay, so this is the... so I've got a box plot here for each competitor, and what each box plot is showing is their scores for both runs combined. So you'll see Nishimura here has this huge wide box plot because, you know, she got close to 0 for the first run, and then she did really quite well. She was actually got some, you know, very well in the second run. Is there anything you notice there that's a bit unusual about the box plots? Well, if you look at the one for Zwetsloot here, the top scorer up there, and for the American Alexis Sablone, you'll see they're both missing a whisker. And that happens because In the case of Zwetsloot, the quartile 3 is the same value as the maximum. And in the case of Sablone, it's the opposite. It's because the quartile 1 is the same as the minimum. So if we look at the 5 numbers, if we look at Zwetsloot at the bottom there, you'll see that her third quartile is the same as her maximum. And that's just an artefact of the scores that she got. And if you look at Sablone, you'll see that her minimum was the same as her first quartile. So it just means that in the case of Sablone, that the bottom quarter of her scores were the same as her minimum. So you will often see box plots where there's missing whiskers. And you will occasionally come across a box plot where there's a missing box. And that happens because the median and the 2 quartiles are the same value. It's basically where you have data where all of the middle is the same value. So you do get these kind of odd manifestations in box plots. But the most common one is probably missing whiskers. Right. Now, I won't have time, I think, today. I'll give it a shot. I'll just introduce it. I think I might do a video about the next bit, rather, because I'd like to have 5 minutes for questions. Do we have any questions? I've covered quite a bit today.
Can you just talk through what is going on in Nishia's schools?
Yeah. So Nishia was the gold medal winner. Sorry? Oh, I see. So what's happening there is her Q3 is very close to her median. So if we have a look at the data here, where is she? Not the data, the 5 numbers. So her Q3 is 3.01 and her median is 3.00. Might help if we go and look at her in the actual data itself. Okay, so there she is. Let's get her up there. Okay. So if you look at her scores, she's got a bunch. She's got one, she's got 3.0, 3.01, 3.05, 3.00, 3.08, 3.0. There's a lot of it's very close to 3.0. So basically what's happened is the upper part of her box on her box plot has just been kind of squished down onto the median. And you'll see that quite a bit too. That sort of thing can happen. Yeah, I think so. Zwetsloot, yeah, well, at one point I thought, Zwetsloot's got it nailed, and then they got to the tricks. So it's an artifact. I don't want to take credit from Nishia, but this system of, so when you do the runs, you get your 5 scores, and then they delete the highest and lowest. And the same with the tricks. And then they average them, I think. And then I think they choose what do they do? You've got 7, you end up with 4 scores that they add up to get the final score. They do some more deleting. I forget exactly how it works. It sounds a bit weird. I have seen this done in other sports, but it's partly I think to prevent judges coming up with extreme scores to try and sway the result. So you get rid of extreme scores. I think I haven't really thought through the mechanics of this, but I think it's actually to keep the competition interesting, to kind of avoid situations where somebody would be obviously the winner after the second run, you know, and the rest of it would just be there'd be no chance of anyone catching up. Because that's what happened. It just all sort of got turned on its head during the, it's kind of.
Who gold medal did you say?
Sorry?
Who got the gold medal?
The Shia Mamiji got the gold medal. And then Raisa Leal got the silver. And I think it was, I think these are in order. And then I think Nakayama Funa got the bronze. Yeah.
What we originally suggested, marketing company or whatever,
Yeah.
looking for someone to do runs, the best decision
Yeah.
would be, based on just the run data, to go with.
Especially, I think so, yeah. Obviously, it's not the only thing you take into consideration. I mean, there's the, you know, country of origin, ethnicity, language skill. There's a bunch of things you might want to. Depends what your market is, but just in terms of, you know, I'd be probably thinking about how good are they and how consistent are they. So if we go back to that last, you know, what you do see in this box plot is there are some people that got, and Rashia was one of these, very narrow range, you know, solid scores, very narrow range. Sablone and Zeng had a wider range of scores. Whether that's something about what they did or something about the judges, I don't know. Because I'm not privy to just how they did the judging. It might have something to do with the rubric, you know, assuming there was one. So, but yeah, I'd probably say, you know, Svetsloot actually sort of really stood out in the runs. So at the end of the runs, I think everyone was thinking, oh, you know, she's got it. Particularly people like me who had no idea how difficult these tricks were that were coming up. You know. Anyway, it was quite interesting. I'd never taken much of an interest in skateboarding. I got a little bit interested in it years ago because I was interested in the photographing of skateboarding, and there was a whole culture of skateboarding magazines and stuff like that. But I've never stood on a skateboard, and I would fall off as soon as I did. But yeah, it's actually I think it's a great